Good morning, Mobile County. I am Mrs. May. I am going to cover 8th grade physical science for you this morning. I'm so glad they put me at 10:30 because that means my teenagers are somewhat awake. Science Alabama Course of Study Standard, apply the law of conservation, blah, blah, blah. Don't worry about that if you can't read it because my boss told me to put that in my presentation for my other bosses. What we actually need to know, though, on this slide is that I'm going to try to refer to page numbers up there at the top right-hand corner for you. That's going to correlate with the packet that you got provided from Mobile County. What we need to know is that today is about energy. Again, if you're following along, we're on page 75 of your packet. We need to know what energy is, however. Energy is the ability to cause change. And in physics terms, that actually means the ability to do work. And I don't mean like, oh, Mom, you're making me do work. I mean work as in a mathematical equation. W equals F times D. And what does that F stand for? That F stands for force. And that D is for distance. So that means that I can put in energy and do work. And then I can actually see that. This word force right here should sound familiar to you. Last quarter we covered all kinds of Newton's laws and forces. But here's the trick. Let's say I have an object here, like this book on the table, and I'm going to put energy into this object. I am only doing work if the object moves in the direction of the force that I'm applying to it. For example, if I lift it up. So I just did work on this book. I put energy into it. Now let's say this book was super, super heavy. If this book was heavy, no matter how much I'm trying or putting in energy, no work is going to be done if I can't move its position. That's where that D comes in, over a distance. So that's the trick there. See? Work is only done if the object is moving, and putting energy into things gets work done. So I would like for you to get a highlighter, a pencil. We're going to take some notes. If you don't have your packet with you, you might want to grab a piece of paper and a pencil. And I just visualized everybody looking to their imaginary social distancing friend they have next to them and say, "Is she serious?" Yes, I'm serious. I had to put makeup on for y'all today. So yes, you are going to get a highlighter, a pencil, and follow along in your packet. So we're going to cover the 6 types of energy. We need to know what we're talking about before we talk about how energy can transform, how energy can change, and where this energy is coming from. So in no particular order, actually in the order from my least favorite to my most favorite, let's start off with nuclear energy. Nuclear energy is found inside the nucleus of an atom, and that might ring a bell because we covered that in chemistry first quarter. Energy is released by those atoms joining or splitting apart. Now that's on the bottom of my list. That's my least favorite. I really don't have any day-to-day use for fusion or fission, but I do appreciate that nuclear energy is a cleaner source of thermal energy for our environment. Actually, it produces no air pollution. Next on my list is electric energy. That's energy that is created by a current. Now, bottom of my list, I appreciate the conveniences of electricity. I just have been shocked too many times as a science teacher, so that's my number 5. Looking at the next type, sound energy. Now, you might think because I'm a teacher, sound energy would be on my bottom of my list, but there are other more beautiful sounds than a bunch of teenagers doing group work all day long. Sound is created, or sound is transferred by vibrating molecules through the air, and that gets to our types of receivers that we have, and we can interpret that as sound. Number 3, thermal energy. Thermal energy is tricky. Thermal energy actually is the kinetic energy of the molecules of matter vibrating around. So the motion of the particles in matter that transfer heat. And I think that's probably halfway on my list of favorites because thermal energy, my favorite form of thermal energy is sitting by a campfire and enjoying that warmth. And my second favorite is radiant energy. You might also hear radiant energy called light energy. And that is a special kind of energy that is transferred by electromagnetic waves. Electromagnetic waves. And that in itself, for Mobile County guys, usually we cover that as a whole objective on its own. Just a quick overview of what that might look like. We have radio waves all the way up to gamma waves talking about frequency. You and I are going to do that in a couple of weeks on our next couple of episodes in detail. But why is that my second favorite? So I have to look at my slide here on the bottom right-hand side if they've got the slide pulled up for you. Oh, I love UV waves. I don't like a sunburn, but I do love my summertime times on the beach. Visible light is on our electromagnetic wave spectrum. Love colors and being able to see things. And then I look at radio waves. Radio waves are a type of radiant or light energy. We don't think of them like that, but radio waves, we get to have awesome music and conversations over social media and things like that with our radio waves. But my all-time favorite, and why radiant or light energy is my second favorite, is because we have microwaves. And microwaves is pretty much the only way my family gets fed. So, looking at number one, drum roll please. Oh, I forget I don't have any kids. Okay, drum roll please. Number one, favorite type of energy is mechanical energy. And that's because that's where stuff happens. That's where things move. That's where collisions happen and all kinds of fun stuff we like to play with outside. Mechanical energy is actually a combination of two types of energy that you probably are already familiar with. It would be the total energy an object has with its kinetic energy and its potential energy. And I'm thinking, your little light bulbs went off there for just a second. Yeah, I remember something about that third quarter. So we had an objective where we looked at the total amount of energy in a system, and that's kind of where we're moving forward to. We're going to move to the law of conservation here in just a second. Let's look a little more closely at kinetic and potential energy though. So when I was thinking about kinetic energy, energy of motion that depends on an object's mass and speed, I was looking for kind of like the epitome of mass and speed, and I sent this text out to my friends in my neighborhood, and my friend John came up with this. He said, here's a picture for you as an example. Now, I don't know exactly who this guy is who's running with the football, but he looks like he has lots of mass and speed, and you see the two other players in the background that he's just kind of running past them. But anyway, he is a great example of mass and speed. Roll Tide. Looking at potential energy is stored energy. That means our object isn't moving yet. Two types of energy that depend on mass and position for potential energy, mass and position. One of which is elastic potential energy. I'm going to move over here to my demo table with my rubber band. And just in case this little puppy pops back on me, I'm going to put my safety glasses on. So I've got my rubber band. And as my rubber band is just hanging out right here, it does not have any elastic potential energy yet. Because if you remember, energy is applied over a distance, or work is done applying a force over a distance. So as my rubber band just sits here, I haven't stored any elastic potential energy yet. But as soon as I start pulling that rubber band backward, now I have stored elastic potential energy. If I keep pulling it back farther, the more distance I pull it back, the more energy I'm going to store. Now, here's something really fun to test this out. So if I'm storing energy and then I release it, what would that look like? Let's think about our last slide. If I'm storing potential energy, I can convert that to kinetic energy, energy of motion. So if I pull the rubber band back just a little bit further, if I let go and release it, shouldn't it convert to kinetic energy? Let's see how good I am. Ready? Thank you for playing. All right. Elastic potential energy. You might also see elastic potential energy in springs, trampolines, where we're displacing or moving that object from its regular resting position and storing that potential energy. Another type of potential energy where I'm storing that potential energy is gravitational potential energy. And gravitational potential energy is the little trick right there is in that first part of the word, gravity. So the work I do against gravity is going to store that object's potential energy due to gravity or its work against gravity. Now, if I were to take a book, for example, going back to our book example, and I were to lift the book somewhat high off the counter. Actually, if the book were on the floor, it would have 0 gravitational potential energy because it has no height off the floor. But I'm going to put some work into this book, and I'm going to lift it up, and now I have done some work against gravity. Now the book has gravitational potential energy. As long as the book is here, it has this amount. If I lift it up higher, objects that are higher have more gravitational potential energy. And I'm going to show you an interactive in just a second about how we can convert gravitational potential energy into kinetic energy. Something fun you can do at home. Looking in my teacher bag of tricks here. There's one, you might have done this in 6th grade. Taking a large, heavy object and dropping it into some Play-Doh or some flour. If I were to look at something really light, like a little ping pong ball, or something really heavy, like this ball bearing, and I were to drop them in the flour, I bet you could guess which one would have more of an impact or transfer that energy. So getting back to our PowerPoint, lastly, a potential energy that was one of my favorites is chemical potential energy that is stored in atoms between their bonds. That sounds really scientific, but what that means is we can eat and get energy out of the food we eat. We can blow up firecrackers and hear the sound, and we can see the light. Chemical potential energy is lots of fun. All right, moving on to our interactive. And I'm going to step over to my computer real quick and pull up a website, pbs.org, and it has a great interactive media on there for you. I'm going to launch it. And one of the things I want to bring to your attention about this particular interactive is it's going to demonstrate really well how this kinetic and potential energy is showing the conservation of a total system, or the conservation of energy in a total system. I want to bring your attention to this circle right here. I think you have been familiar with a pie chart. That's what this is going to show. I'm going to read these off to you so you can see what we're looking for. The red is going to be potential energy. So just to remind you real quick, potential energy is stored energy. In particular, we're going to be looking at gravitational potential energy. Then we have kinetic energy. And if you think back to the football player picture, we're looking at the kinetic energy of motion. Now this whole circle, if you think about I've got 100% or I have 360 full amount of my whole energy in my system is going to be conserved within this whole roller coaster ride. So I want us to predict a little bit. I'm going to have the roller coaster go up to the top of the hill. Now, if we think about gravitational potential energy and height, going back to my book, the higher we are, the more gravitational potential energy we have. I want you to predict what color do you think this whole circle is going to be if potential energy is shown in red and kinetic energy is shown in blue. I'll give you a second to think about that. All right, I'm going to click play. So here we go. Let's see if your prediction's right. Oh, there we go. At the top of the hill, we had a full red circle that showed that it's potential energy. In case you missed it, I'll do it step by step. So here we have the roller coaster going to the top of the hill, and just before we take all of that potential energy and spend it into kinetic energy, our circle is all red. Now at the bottom of the hill, let's predict. At the bottom of the hill, has anybody been on a roller coaster before? Really intense. I love it. You really feel those G-forces right here at the bottom. So I wonder what that means for kinetic energy. And I wonder what that is going to mean for our pie chart here. Give you a second to think about it. And I'm going to click play. And there we are. So as you can see, potential energy is converted into kinetic energy. And I'm going the fastest I can go at the bottom of this hill. Remember, kinetic energy is your mass and speed. I'm going as fast as I can, as fast as I can, the most speed at the bottom of this hill. And I can imagine you could look at this on your own on pbs.org. Let me just play it step by step for you, just in case you were curious. Here we go through our loop-de-loop. Again, look at, I'm going back a little bit higher now, so I've got some of my gravitational potential energy back. Still going pretty fast though, I've got some kinetic energy. Oh, there we go. And finally, we're done. All right, going back to our PowerPoint. Thank you for being patient. I want to do another demonstration for you. You might have seen one of these before. This is called a Newton's Cradle. And the Newton's Cradle is great for a lot of demonstrations. A lot of information can come out of Newton's Cradle. We're going to look at it as far as energy input and energy transfer. All right, so does this look okay, guys? Okay, all right. So Newton's Cradle is really a neat demonstration tool. Now I want you to try to apply what we have learned with the roller coaster interactive and the types of energy that we've had to our Newton's Cradle. So if you think about what we've talked about, I'm going to take the ball on the right-hand side and I'm going to lift it. Now think about this. I'm doing energy, I'm applying energy, I'm doing work because I'm moving the ball out of its resting position and I'm actually going up against gravity, so I'm gaining some gravitational potential energy. And just like the rubber band has some stored potential energy and then we released it, it converted to kinetic energy. And our roller coaster interactive, we had that stored potential energy on top of that hill and we converted it to kinetic energy. I can lift the ball, putting energy in, doing work, and when I release it, it actually transfers that energy to the balls on the middle, and then that ball on the right hand, or my left hand side, your right hand side probably, is going to lift up in reaction. Now I'm going to do that for you again because I want you to pay attention to something that we're moving on to that's really important. Going back to this conservation of energy. If I lift the ball on this side up about that high, then I want you to watch how high this one goes when I let it go. Did you see that? How about if I lift this one a little bit higher? Does this one go higher? Sure does. And actually, if you take a ruler to it and you can get something fancy like a slow-mo camera or slow-mo video on your iPad, you can actually put two rulers side by side and see that when this action, this should sound familiar, when this action is applied, we have an equal and opposite reaction on the other side. We just have to do something fun here. My daughter showed me this. So if we lift two at the same time, what happens, right? I love science. Science is what if, isn't it? I love it. What if? All right, what if I lift two? What would happen? Would one ball go off to the side? I don't know. Let's see what happens. Cool. There's all kinds of fun stuff you can do with the Newton's Cradle. But the main idea behind our Newton's Cradle today is that energy is conserved in the system and that the energy is converted and transferred from one object to the next, and then for every action there's an equal and opposite reaction, putting energy into that. Now, here's something that I learned new. At one point I thought that if I lifted up this ball and I hit the ball into there and this constant reaction would happen, it would just keep going forever. But there is something that's a real drag here on Earth, friction. So we have another thing to take into consideration with matter and its interactions on Earth. We have to take into consideration friction. And there is no movement on Earth without friction. Friction is a resistant force to an object in motion. So as soon as I lift this ball up and it collides, there's a tiny little amount of friction between this ball. When this ball transfers energy to the next one, a little bit amount of friction, and so on and so on. And you have to keep in mind that as the ball moves through the air is also applying fluid friction back on the ball. So eventually, they're going to stop. Eventually, they're going to slow down. Eventually. All right. That still doesn't go against what we're trying to say about the law of conservation. It just means that that energy is converted into heat energy due to friction. Maybe you had a 4th grade science teacher have you put your hands together and rub your hands back and forth and feel the heat that is produced from friction. So, just to summarize, we've got our 6 different types of energies. We're going to pick up next episode with talking about energy transformations and the way that we can conserve that energy and transfer it from one type to another. And I just want to leave you with kind of a mind, like a little mind inquiry thing. And here we've got what is called a hand generator. Because we live on the Gulf Coast, I bet you have seen a flashlight that has a crank or a radio that has a crank to it. This one's really cool because it's see-through. This is going to, I'll just crank it for us. Let's just see what happens. So as I turn it, the light bulb turns on. But the energy going into this little contraption wasn't electricity, yet that's the type of energy that I'm getting out. So that's where we're going to pick up for the next episode. And I would like to do a lab with you to show you how kinetic energy can cause change, and we'll get some data in a chart, and we will actually calculate it and try to interpret some of our data, maybe even make a graph. So I really appreciate you having me today. It is just really a nice way to have an outlet for me to be able to come into your homes today and be there with you. And hopefully I will see you next Wednesday at 10:30.